Welcome to Thermodynamics. This video will give you just an overview of what we're going to learn and go through some of the definitions in Chapter 1. So first of all, thermodynamics, what we're studying here, describes basic macroscopic properties of equilibrium systems. There is a microscopic level of thermodynamics, and we do touch on that in a few chapters, but what we're talking about here is really the macroscopic properties of equilibrium systems. And thermodynamics in this case is entirely empirical, meaning that none of the theorems can be proven outright, but have been shown by taking data and looking at actual systems to be appropriate. So they're empirical in nature and not derived, if you will. Thermodynamics is built on four laws and some basic mathematics. These laws cannot be circumvented. So the 0th law is sort of the defines temperature, and we'll get into that one later in this chapter. But it basically tells us defines temperature and temperature scales. The 1st law defines energy and conservation of energy. And the 2nd law, it defines entropy, and we learn that time moves in one direction. The 3rd law gives empirical values to entropy, so continues with entropy. We will touch on the 3rd law, cover the 1st and 2nd laws primarily in this class. So we have a lot of definitions, but we need to be able to do thermodynamics, and so this chapter we have some basic definitions. But the system is whatever we are choosing to study. So it could be me or you, a human body. In other words, it could be a thermos filled with hot water and sealed. It could be a cup of coffee, a glass of ice water, but it also could just be 4 cubic centimeters of the air around us. It doesn't actually have to have a physical boundary. And we'll get to the definition of boundary in a second, but what we're talking about in the system is whatever we're studying. It could be a single element of a system, or it could be a whole power plant, for instance. The surroundings are whatever is external to the system. So if 4 cubic centimeters of air in the middle of our room is our system, then all the rest of the air in the room and the outside of the house and the outside of the in cosmos and the moon and everything else external to that 4 cubic centimeters in the middle of your room, that is the surroundings. So the surroundings is anything that is not the system. And then the boundary is just the surface dividing the system from the surroundings. So for instance, if we are looking at the human body, your skin would be the boundary. Everything outside of the human body would be the surroundings, and everything internal to the human body would be the system. Sometimes we call this surface the control surface, and it defines the system essentially, separates the system from the surroundings. So there are different kinds of systems. We have a system, closed systems, and open systems, or sometimes called control volumes. But first of all, closed system, where mass is controlled. This is energy can be transferred between the system and the surroundings, but not mass. Mass cannot be transferred through a closed system. So you get a fixed quantity of matter, and energy transfer may occur by work or by heat transfer. So for instance, if we had a glass of water, ice water, and we put a lid on it, that would be a closed system. Energy would flow, the water would eventually reduce its temperature. The glass may even, in fact, get condensation on it, that's coming from the surroundings, but energy will transfer as that temperature decreases, but no mass would flow out of that. You wouldn't lose any of the water that's actually in the glass. An isolated system is a special kind of closed system. It's the opposite of an open system. So in isolated system, neither mass nor energy can transfer between the system and the surroundings. It does not interact with its surroundings. No heat transfer or work can happen. Mass remains constant. Temperature may in fact change. Pressure may change. But an example of this would be a closed thermos. So we have the thermos, and differently than the glass of ice water, where the ice interacts, the glass interacts with the surroundings. A thermos is insulated, and so it doesn't interact with the surroundings. So if we have an isolated system, then it is insulated from the surroundings. And control volume is another way to say open system, and mass and energy can be transferred between the system and the surroundings. The region of space through which the mass may flow, it makes it an open system. So thinking about a control volume, and thinking again about, like, let's say a human. So a human is an open system or control volume. So even though you have skin, your skin actually breathes, you sweat. Sweating would be mass transfer across the body boundary. You can also take in food across the boundary through your mouth. We also eliminate, which is another way of mass transferring across the system's boundaries, if you will. Anyway, so that's an open system. We'll see later that any system where there's flow, whether that's water flowing through a system or some kind of refrigerant or something like that, that would also be a control volume system. So there's two different kinds of control volume systems. There's a steady state operation. During a steady state operation, no system properties change with time. So we take measurements of temperature, pressure, volume, things like that, and then we take them again at a different time, and there is no change in that. That's steady state operation. Transient operation, property values, work and heat transfer rates, and mass flow will vary with time. So we can take those measurements at one point and then at a different point in time, and those measurements would in fact change. So describing a system requires a few macroscopic properties. We describe a system using pressure, temperature, volume, moles, mass. Those are different ways to, different properties under which we can define or describe a system. Systems can be either homogeneous or heterogeneous. So a homogeneous system, you have everything in the same state. So everything's either liquid or everything's solid. So thinking about like a cup of coffee with cream in it, or some kind of fancy coffee, that is still a uniform one-phase system. It's all liquid, it's all mixed up. That is a homogeneous system. Heterogeneous system, you would have two different states. So you may have liquid and solid. For instance, a glass of ice water would be heterogeneous state. If a system's in an equilibrium state, then we can describe it using thermodynamic properties. It doesn't change, it's uniform throughout. If it's in equilibrium state, it isn't changing. But the number of components, so in a glass of ice water, which we said was heterogeneous, right? You have ice and you have water. That's a heterogeneous system, but the number of components in that heterogeneous system is just one. There's just H2O, both in the ice and in the water. The homogeneous system that we described, where we had a cup of coffee, where you had coffee and milk and maybe even sugar all blended in together, but it's all still a liquid state, that would be homogeneous, but the number of components would be multiple, or 2, 3, 4, however many components went into that particular cup of coffee. So some more definitions. A property is a macroscopic characteristic of the state system, such as mass, volume, energy, pressure, temperature. Anyway, these characteristics to which a numerical value can be assigned at a given time without knowledge of previous behavior or history of the system. It's independent of process. So we don't really care how it got here. We don't care that the temperature in this room is 72, or, I mean, we care that the temperature in the room is 72. We don't care how it got there. We don't care the process it went to get to 72. We just care about the property that it is 72 degrees, if you will. That's what a kind of property. How much mass does it have? How much volume, energy, pressure, temperature, and so on. Non-properties are depend on the details of the process and are not solely on the endpoints. So mass flow rate, energy transfer by work or heat, those are non-properties. State refers to the condition of a system as described by its properties, the value of properties of a system at a given time. Because there's a relationship among the properties, the state is often satisfied by a subset of the properties. All other properties can be determined by this in terms of this subset. So what this means is that we define a state of a system by its temperature, its mass, its volume, its pressure. But those things are all related in different ways. And so we have a subset of those, we can use our tables to find the other values. So anyway, mass, volume, energy, pressure, and temperature are properties that describe a state. There's two classes of properties. We have extensive properties, which depend on the size of the system. The value for the overall system is the sum of the values for the parts into which it is divided, the system is divided. So what this means is if I have a certain volume and it has a certain mass to it, and this is my system, now I double the size of the system, then I double the size of the mass, double the size of the volume, and so on. That's extensive properties. So extensive properties depend on the size of the system. If I have my 4 cubic centimeters or cubic meters of air in the middle of this room, and then I double that, now I've doubled the volume size, doubled the mass, and so on. That's an extensive property. So it's dependent on the parts. I think in your book they have a barbell system, and they say that the mass and volume and all this is the sum of all of the bar and all of the different weights that are put on the barbell. That's an extensive property. Intensive properties are independent of the size and extent of the system and may vary from place to place within the system, but it's not additive. So thinking about temperature. So if I have my 4 cubic meters of air in the middle of the room, that air has a certain temperature associated with it. If I double the size of that volume of air, I don't double the size of the temperature. The temperature doesn't double. It may change a little because you may have cooler air next to hotter air and they blend somehow, but it would be very small amount of change between them. It definitely doesn't double by doubling the volume. So temperature is an intensive property. So it's specific volume and pressure. Process is the transformation from one state to another. We'll learn more about that in subsequent chapters too. Steady state, if none of the properties change, the system's property change with time. If the system exhibits the same values of its properties at 2 different times, it is in the same state at both of these times, thus it's steady state. State of system at equilibrium, several types of equilibrium. There are several types of equilibrium: mechanical, thermal, chemical, thermodynamics. The way we test for thermodynamic equilibrium is we isolate the system from its surroundings. So again, to isolate it, we insulate it so that there's no heat transfer or energy transfer across its boundary. So we take our system, we isolate it, and then we watch for any observable changes in properties. If there is no change noted, we conclude that the system is in equilibrium or was in equilibrium at the time we isolated it. So if the properties aren't changing, if our temperature doesn't change, if our volume isn't changing, if our mass isn't changing, and so on, then we conclude that that is in the equilibrium state at the moment it was isolated. Specific volume, so volume is a capital V. Specific volume, we divide the volume by the mass of the system, the volume of the system by the mass of the system. It's an intensive property, meaning that it's not additive, and it's defined also by the reciprocal of density. So density is the rho, and specific volume is a little v, and little v is 1 over rho, or the reciprocal of density, which is also equals the volume divided by the mass. You may recall from chemistry and some other things that density is mass divided by volume. So again, it's the specific volume is the reciprocal of that. So pressure, unless otherwise noted, pressure refers to absolute pressure, and pressure with respect to zero pressure of a complete vacuum. The lowest possible value of absolute pressure is 0. And we find pressure as the pressure at 1 atmosphere, atmospheric pressure, P sub ATM. That is the local atmospheric pressure. And then we add to that the density times gravity times L, which is the difference in the liquid levels. We'll talk more about that in class. Buoyant force is the force of a body submerged in liquid. Pressure increases with the depth from a liquid surface. Pressure forces from below and an object are greater than from above. Thus, buoyant force acts upwardly vertical. F, which is that buoyant force, equals rho, which is the density, times G, which is gravity, times V, where V is volume, again area, times that change in liquid levels. Gauge pressure or vacuum pressure. So we use gauge pressure when the pressure of the system is greater than atmospheric pressure. So then we use the pressure of the gauge equals the absolute pressure minus the atmospheric pressure, the absolute atmospheric pressure. We use vacuum pressure when the local atmospheric pressure is greater than the pressure of the system. So the pressure of the vacuum equals the atmospheric pressure minus the absolute pressure. So these should just be positive. So dependent on which one is bigger, then we use one or the other of these two. Okay, so here is our 0th law, thermal equilibrium. Thermal equilibrium is when heat stops flowing. So if we have two objects, object A is hot and object B is cold, and we put them together, and they become in thermal contact, so they're touching, the heat will flow from the warmer to the cooler object. This will continue until they're in thermal equilibrium. That's when the heat stops flowing. At this point, both bodies are just said to have the same temperature. This is intuitively straightforward idea and is formalized as the 0th law of thermodynamics, and is made practical through the development of thermometers and temperature scales. So this is how we define the 0th law, and the 0th law effectively gives us the concept of a thermometer. So the 0th law of thermodynamics, if A and B are in thermal equilibrium, and B and C are in thermal equilibrium, then A and C are also in thermal equilibrium. And so we say that B is acting like a thermometer, and that A, B, and C are all at the same temperature. That is the 0th law of thermodynamics. It's also sometimes called the common sense law. So temperature, it's an intensive property. Again, it's not additive. We don't add up the temperature. If we double the volume, we don't double the temperature. There are different temperature scales. There's actually quite a few. The ones that we will look at are Kelvin, Rankine, Celsius, and Fahrenheit. So the absolute thermodynamic temperature scale is the Kelvin scale, and is the absolute thermodynamic temperature scale, whose units of temperature are in K or Kelvin. This is an SI base unit for temperature. Rankine is the absolute thermodynamic temperature scale with absolute zero that coincides with absolute zero of the Kelvin scale, and English base unit for temperature. So these Kelvin and Rankine are the two absolute thermodynamic temperature scales. And then the other two that we have are Celsius and Fahrenheit. So Rankine, temperature in degrees Rankine is 1.8 times the temperature of Kelvin. The temperature of Celsius is the temperature of Kelvin minus 273.15 degrees. That gets you from Kelvin to Celsius. And then Fahrenheit, we go from Rankine, we subtract off 459.67 degrees. And then another way to find temperature of Fahrenheit in relation to Celsius is to take 1.8 times the temperature Celsius and add 32 degrees. Those are our temperature formulas.